Assalamualaikum warahmatullahi wabarakatuh and good day to all. My name is Muhammad Harizan bin Zul from University Malaysia Pahang. Today I will present the title of my study, which is the influence of laser power in nanosecond laser texturing for a hydrophobic state on stainless steel 316L. The following is the content of my presentation covering the introduction, objective, methodology, result and discussion, and also the conclusion. Without delay, I proceed to the introduction. This is the overview of the background of this study. The sample will undergo a laser texturing process using nanosecond laser pulse power. Theoretically, this process applies the laser method by ablation. Surface modification has various industrial applications such as wetting behavior, corrosion resistance, strengthen the material adhesion, and control the friction. Most industries prefer to use more advanced and fast laser technologies such as femtosecond and picoseconds. But they are costly and not very economical, while the nanosecond laser technology is versatile and simple to shape. Many parameters, of course, need to be optimized to achieve the best machining performance. Laser texturing methods have various benefits such as flexibility, accuracy, chemical-free processing, lack of tool use, and minimal impact on bulk materials properties. Many studies on laser-structured metallic surface show changes in hydrophilic properties to become hydrophobic over time because of absorption from the atmosphere. This laser texture process is using a laser ablation method. In a pulse laser ablation process, stainless steel melts to a temperature where the atom gains sufficient energy to enter the gaseous phase. Because of the laser pulse energy absorption, the molten materials expelled from the cavity because of the vapor and plasma pressure and form surface debris. At the end of a pulse, the heat quickly dissipates through the bulk of the substance and the recasting layer is formed. Apparent contact angle surface above 90 degree defines as hydrophobic surface. In contrast, superhydrophobic surfaces have a higher water contact angle than 150 degree and contact angle less than 90 degree known as the hydrophilic surfaces. The objective of this study is to determine the relationship between surface topography and the water contact angle of 316L material is discussed. The material used for the study is stainless steel 316L. It widely used. The laser device system structure is shown in figure 2, with also the machining parameters I explained in table 1. The study focused on laser power output and the rest is fake. Next, the surface topography was observed using LEX, Olympus OLS 5000 3D laser scanning confocal microscope. Standard surface roughness information such as RA, RZ, RSM with advanced surface parameters such as RSK, Qness and RKU kurtosis was calculated. Contact angle measurement were performed on a custom system device as shown in figure 3. The recorded image will be determined by the contact angle via the ImageJ software using the drop analysis plugin. Table 2 display the RA and RZ values from untreated and laser treated samples from surface roughness profile. Both RA and RZ values increase after laser treatment. The additional surface parameter were quantified by RSK and RKU. These two parameters play an important role in providing a characterization of the surface. Qness serve to determine whether the surface profile is matched against the spike or valley. In contrast, kurtosis will determine whether the surface of the material is flat or peaked. The finding of skewness and kurtosis show that untreated material has a bumpy base surface. In contrast, the laser texture surface shows the valley effect and give a positive reading of skewness. So the surface has more peaks than the abundance of peaks. The surface profile of laser-treated surfaces is shown in Figure 4. As observed, all laser-treated surfaces show a horizontal area affected by laser ablated. The depth of laser texturing result in Table 3 also shows that at laser power 12 and 24 watt give depth 22 and 24 micrometer respectively. The laser fluence is calculated by given equation above. Figure 6 presents the water contact angle of untreated and laser-treated samples. From the result, untreated samples have a contact angle of near to 50 degrees, suggesting the hydrophilic condition at all times. On the other hand, laser-treated water contact angles are found improved from hydrophilic at day 1 to be hydrophobicity at the end of 30 days. This also shows that the surface hydrophilicity of 316L is much improved after laser texturing. Furthermore, the increase in the contact angle is more profound for laser treated with the higher laser power. The previous study by Chai et al. Has found that one-dimensionless functional parameters which help assess the surface contact angle, namely RHY, which can be computed from the RZ average ratio to RSM. The result on the calculation of RHY parameters are explained in Figure 7, where it shows that the highest RHY value able to produce a hydrophobicity state. The weighting model can be explained graphically as shown in Figure 8. Based on the current model Cassie-Baxter, the droplet cannot access the spaces of the microstructure. The deep valley also contributes to forming stable air trap or air pockets underwater droplets, which creates superhydrophobic spaces. Therefore, adequate depth of the microstructure is necessary for the Cassie-Baxter water droplet condition. Both Wenzel's and Cassie contact angle model are closely linked to surface topography. The gaseous phase entrapment will increase the contact angle as shown in Figure 9, even if the hydrophobic surface is preferably smooth. Besides, it can be concluded that too rough surface got in this work with the nanosecond pulse laser entanglement do not allow the quick reduction in the angle of contact angle with water as expressed by Wenzel. A nanosecond laser texture on stainless steel 316L was studied to affect the hydrophobicity of laser power and surface roughness. The maximum contact angle can be achieved is 125 degree with the output power of 24 watt and calculated on the day of 13/30. As a conclusion, 1. The laser power output has an enormous influence on contact angle as the surface roughness increases. 2. RHY parameter is a unitless parameter that can be used in detailing the surface topography. The contact angle can achieve hydrophobicity from RHY increase as a sign for a wettability change. And number 3, kurtosis and skewness are also a useful parameter for hydrophobicity signal. With the increase of RSK and RKU under the same microstructure pitch, the contact angle will increase. Then the height value of RSK and RKU means more spaces for the droplet to settle. The creation of an air trap or air pocket in the water droplet on the specimen surface in the state of Cassie-Baxter helps to transform hydrophobicity condition. That's the end of my sharing session. With that, I thank